Hello everyone, welcome to Dr. Ravi's Academy. In today's virtual class, we will be learning a topic simple stresses and strains. So this is a topic from mechanics of solids and which is of course known as strength of materials also. This is the very first lecture of this particular subject. So in this particular lecture, you will be understanding the various types of stresses, and these stresses also known as direct stresses, tensile stress, compressive stress as well as shear stress. And let us observe carefully, generally sigma is used for normal stresses. These two are normal stresses, and subscript T is used for tensile and subscript C is used for compressive. Of course, it is a shear stress. And let us look at this. First of all, let us understand what is meant by simple stress. When a body is subjected to only one type of loading and the stress developed in the material is known as simple stresses, and practically this is not possible. Only for experimental purpose we will be learning this, and usually you will come across with the combinations of stresses, that is direct and indirect stresses. And it is in this particular class we will be understanding the three types of stresses, that is tensile stress. The first type, let us look at this tensile stress by means of a diagram. Let us look at this diagram. I am considering a slender bar of diameter D. This diameter is D and length I am considering L. L is the length of the bar. So this is subjected to a load away from the body, that is pulling load. It is the load leads to extension of the bar. So because this load, the length is increased in such a way that that particular type of load is called tensile load, and the stress developed in the material is called tensile stress. So here you can see that there is an extension of a bar. So L plus delta is the length of the bar when it is subjected to loading. That means there is an increase in the length by extension delta. And observe carefully, there is a decrease also. There is a decrease of the diameter, and you can see that decrease in diameter, I am calling it as D1. D1 is the decrease in diameter, initial diameter is D. So this is what exactly the given configuration when it is subjected to a load such that the length of the bar is extended. So when the load leads to extension of the bar, such type of load is called tensile load, and the stress developed in the material is called tensile stress. So let us consider a section MN at certain distance from the top and draw the free body diagram of top portion up to MN section. So when there is a load acting upwards, the resistive forces are developed in the material. That resistive forces are, it is acting downwards. The fiber of the material will be developed, and the resulting of all this, sum of all this is resistive force R. R is the resistive force developed in the material. And now you can write down the definition of tensile stress. Here the symbol is sigma T. It is nothing but it is the ratio of the resulting resistive force divided by the area, that is cross section area, that is pi by 4 d square. Here A is pi by 4 d square is the cross section area, and you see that it is perpendicular to the direction of the loading. That is what is normal stress. And this R is equals to, because this is in equilibrium, your R is equals to P, you can write down the external load P divided by the cross section area. And units are, it is Newton, the forces are in Newtons, and your area in usually in mm square. So you have a conversion factor for this. So it is Newton per mm square. You can rewrite it as Newton. You can convert this mm into meters by 1 by 1000 whole square into meter square. You know very well that Newton per meter square is Pascal, and this 10 to the power becomes 6 and that goes up, it is 10 to power 6, it is pascals. 10 to power 6 is nothing but megapascal. So 1 Newton per mm square is equals to, it is 1 megapascal. 10 to the power 6 is nothing but megapascal. This is the conversion factor or units usually used, and you will be using even gigapascals also. Giga is nothing but it is 10 to the power 9. 10 to the power 9 is gigapascals. So this is what exactly the concept of stress. So after understanding the concept of stress, let us look at the change in dimension, that is strains. First you consider there is an increase in the length of the bar by extension. I am using a symbol epsilon. Epsilon is the symbol for the strain and it is the ratio of the extension of the bar to initial length L. So both are in millimeters, and this particular quantity, or you don't have dimensions, it is a dimensionless quantity. So mm divided by mm. So this is a linear strain. So when the length is increasing, obviously there is a decrease in the diameter, the lateral dimension diameter. So you can write down the lateral strain also. I am using a symbol, epsilon LA for lateral. It is the ratio of change in diameter. Initial diameter is D and change it to D1. So I am writing it as D minus D1, change in diameter to initial diameter. This is what exactly the lateral strain. Once you know the linear strain and the lateral strain, Poisson proposed a relation between these two strains. It's called Poisson's ratio. It is a Poisson's ratio. You can define it is the ratio of, it is usually represented by 1 by m, or even mu is also being used. This is equals to, it is lateral strain, that is epsilon LA, to linear strain, that is epsilon. So the ratio of these two is known as the Poisson's ratio. Now we have understood the linear strain. Linear strain is also called axial strain as well as longitudinal strain also. Here lateral strain, and let us understand, once these two are existing, if you consider it is x-axis and along the load it is y, and perpendicular to it, it is z-axis, xy z-axis. As you know, the volumetric strain epsilon v, I am using a symbol subscript v for volumetric. This is nothing but it is algebraic sum of the linear strain in x direction and the linear strain in y direction as well as the linear strain in z direction. Observe carefully, your linear strain is along the y direction. So this is your simply epsilon, whereas epsilon x as well as epsilon z are lateral strains, and there is a decrease in the dimensions, and because of that we will be using, it is mu times, it is lateral is equals to, it is mu times, it is linear strain will be using, and here again this is also same, and you have it is mu times minus 2 times mu epsilon, and this you can write down the expression for the volumetric strain as if you take epsilon common, that is linear strain, it is 1 minus 2 mu. This is one very important relation between the volumetric strain and the linear strain. I hope you understood the concept very clearly, the tensile stress, the definition and the units as well as the strains involved in this. Now let us look at another loading, that is compressive loading. It is a compressive stress, that is second type of stress. When a member is subjected to load such that the length of the member is shortened, reduced. Initially length L you have, and because of the loading the length is reduced so that the lateral dimensions are increased. So this is the change in the dimensions. I am showing by dashed lines. You can see that, and this is a change in dimensions, and this is the initial length L. Right? Now you can consider the free body diagram at a section. It is Mn, and here the stresses developed, or you can draw the free body diagram from top to Mn section. Right? and here it is acting downwards, the P is acting downwards, the resistive forces opposite to the direction of the loading are developed in the material. This is the resultant resisting forces, sum of all these forces, and now you can define the compressive stress sigma C. The subscript used is C. Normal stress sigma and compressive stress, and this is nothing but R by the cross section area A, and R is equals to the external load P by A, and of course the units are Newton per mm square, and the same thing whatever we have analyzed here, it is applicable to compressive also. Now let us understand the third type. This is your second type of stress. This is the first type, that is tensile compressive, and let us look at the shear stress also. Third one is shear stress, that is tau, that is shear stress. For this, let us consider a plate of dimensions. Let us look at this, this dimension I am calling it as L, and load is acting on this P, and this particular surface is having, I am calling it as area is AS, and dimensions are B into T. Let me show pictorially. It is having a dimensions of BT, right. So this dimension, this is B and thickness is T, and load is acting along the area. This is what is the tangential load P, and here it is fixed and fixed. This is what is the configuration diagram, and when the load is acting per tangential, the shearing area is BT. Now you can write down the expression. The symbol used for shear stress is tau. Tau is equals to the load, tangential load, that is P divided by the bearing area or shearing area, and of course the units are, it is again Newton per mm square. I hope you understood the types of direct or simple stresses, that is tensile stress, compressive stress, as well as shear stress. Thank you for watching this video.